In this segment, I'm going to talk about circulatory systems and internal transport. So heart can be as simple as a blood vessel that has muscular thickening and one-way valves. Those one-way valves serve to cause blood to move in only one direction. Let's look at what happens with contraction. Let's imagine we have one-way valves that can be open or closed, and if we have contraction happening such that this starts to get squeezed, then we're going to put pressure on the fluid in all directions. These backward valves are going to be pushed closed. This back pressure pushes back on the valves and pushes them closed. The forward pressure pushes these open and out of the way, and so blood or hemolymph will move forward. So next, what happens when these relax? So the muscle relaxes. The result is that the walls move back to their earlier position. We've pumped fluid out under pressure, and so as the pressure lowers, back pressure is going to push these valves closed. So the fluid we just pumped out under pressure create back pressure, which forces these valves closed. In contrast, this lowering pressure allows new blood or hemolymph to come in and refill. The result is a cycle in which we first compress this and we force blood out. That's part one. And then part two, this relaxes. The result is back pressure forces these closed and new blood comes in. So let's think about this for a simple fish heart. And in a fish heart, we have two chambers. In both cases, it's a muscular tube with one-way valves. The lower one is the ventricle, and the upper one here is the atrium, A for atrium, V for ventricle. The wall of the ventricle is thicker because it's going to send blood out to the whole body. It's a relatively thin muscle because all it has to do is fill the ventricle. And notice the one-way valves at each point that I've labeled with small v's. So in the cycle of contracting, we have atrial contraction, which just fills the ventricle. So we've got contraction is pushing in here. The back pressure forces those valves closed, and it pushes the blood into the ventricle, and notice the ventricle is expanding. The ventricle at this point, these valves are closed because from the previous heartbeat, back pressure is pushing those closed. Once the ventricle is full, the atrium relaxes. Now back pressure pushes these valves closed as the ventricle starts to contract. So these valves close, but these valves are open, so the atrium refills. The ventricle at the same time is emptying because this contraction pushes these walls in further and further. The blood can't go backwards. It all has to leave. Each cycle is first the atrium contracting and filling the ventricle, then the ventricle contracting, allowing the atrium time to refill and pushing the blood out, and then it starts over. Most fish have an atrium and a ventricle. The fluid is going this way. The atrium fills the ventricle, the thicker-walled ventricle pushes blood out, and then here are the gills where gas exchange will take place. From there, in most fish, the blood goes out to the capillaries in most of the body or to the capillaries of the head. In arteries, to arterioles, to capillaries, the head, venules, veins, and back. Arteries to arterioles to capillaries all through the rest of the body, and then back to the largest veins and back to the atrium. I also want to distinguish between closed circulatory systems and open circulatory system. In a closed circulatory system, the blood is always within tubes, from arteries to arterioles to capillaries to venules to veins and back. In an open circulatory system, you still have a heart, blood goes in arteries, but then those arteries or arterioles just open up, and the fluid is now called hemolymph instead of blood, because in animals with closed circulatory systems, you have lymph that is the same as the extracellular fluid, and blood that always stays within the circulatory system. But in an open circulatory system, such as in an insect or an arthropod, the fluid is leaving the blood vessels and going between cells before going back to vessels, and so the blood, hemo, is the same as the lymph. So we call it hemolymph. We're going to be talking about hearts, so I want to show you how to draw a heart. People struggle with answers to exam questions because they can't remember a quick way to draw a heart. Here's the first step, so that's 1. Then draw 3 parallel lines going about halfway down. That's 2. Draw valves, one-way valves here. That's 3 and 3. And blood vessels coming in. That's 4 and 4. Atria. And you need one-way valves going to the ventricle, and that's 5. There are one-way valves going out, and that's 6. And blood goes to the lung or to the system. For birds, crocodilians, and mammals, start exactly the same way, but the difference is a divided ventricle. The right atrium, the right ventricle, the left atrium, the left ventricle, and a way to recall where it's going, right to lung, and the left then to the system. The blood coming in is from the lung, and so that low oxygen blood is going to the lung. Okay, so that's how to draw a heart. And now let's talk about the blood flow from the system in the lung, and in this case we're talking about amphibians and most reptiles. Contracting deoxygenated blood from the system, moving in to this area in an amphibian or a reptile heart, whereas the oxygenated blood is filling this area. As the ventricle contracts, it closes these valves, but the system has higher pressure than the blood to the lungs. And so as the ventricle starts to contract, it only has enough pressure to push open these valves to the lung. And remember I said that this is the area that has deoxygenated blood, and this is the area that has oxygenated blood. So in an amphibian or reptile, even though the ventricle is not divided and the blood could mix, the shape of the heart and the location of the blood forces the deoxygenated blood to the lung. As contraction continues, we've moved most of the deoxygenated blood out, but there's still some left in here. But now the pressure is high enough inside the ventricle that we start moving blood to the system, and it's mostly the oxygenated blood. Again, the shape of the heart and the location moves mostly oxygenated blood to the system. Why have a divided ventricle? Reptiles and amphibians can go a fair amount of time without breathing, and if they had to force blood through their lungs throughout that whole time, they're getting no benefit. If they're not breathing, sending blood through the lungs is a waste of resources. What an amphibian and most reptiles can do is when they're not breathing, they constrict the blood vessels here so that almost no blood can go to the lung. Under those conditions, oxygenated blood and deoxygenated blood goes to the system. Amphibians and reptiles don't use oxygen that fast, and so even this deoxygenated blood still has some oxygen. They may as well save energy, not send blood to the lung, and send all the blood to the system. There's mixing of oxygenated and deoxygenated blood, but there's some oxygen in deoxygenated blood even after multiple passes through the system. The mixing is worthwhile if the animal is not breathing. What about birds, crocodilians, and mammals? Deoxygenated blood is coming in from the system and oxygenated blood from the lung. The ventricle is completely divided. In the first part of the cycle, we fill the atria. Then the atria expel blood into the ventricles. So when the ventricles start to contract, all the deoxygenated blood goes to the lung. We force these valves closed, and all the oxygenated blood goes to the system. There's no mixing, and there's a second advantage when the pathway of the blood from the heart to the lung is quite short, and if we had an undivided ventricle, that would send blood to the lung at only slightly lower pressures than to the system. The completely divided ventricle allows reptiles and birds to have much higher pressures in the system, 5 to 7 times the pressure compared to the pressure here is, say, 150 millimeters of mercury, this might be 30 millimeters of mercury, which is perfectly fine to send blood to the lung. There's enough pressure, and it's not so high that it causes fluid leakage into the lung, edema. This much higher pressure moves the blood fast to the system, and because it has to go so far through all the arteries, it's at low, safe pressures by the time it gets to the capillaries. If you're an amphibian or a reptile, an undivided heart means you can more efficiently move your blood when you're not breathing, but you can't have the high pressures for really fast blood through the whole system. In contrast, if you're a bird or a mammal, you can have higher pressures in your ventricle to move blood fast to the system and low to safely move blood to the lungs at lower pressure.